Hello all, welcome to this lecture and we will continue our discussion with the special motor drives. So in the previous lecture we have seen the operation of the magnetic plunger with a C-core electromagnet. So here electromagnet is having soft magnetic material and we are having a movable plunger which is hinged at one point. So whenever excitation is provided to this coil, the flux lines generated within this electromagnet will link the plunger and the plunger will have tendency to move towards the C core. So there are two possibilities for the plunger to be in. One, when it is far from the electromagnet, say the condition when it is unaligned with respect to the electromagnet, and this is where we have the inductance value minimum in the compared to the other scenarios, and in the other position when the plunger has completely moved towards the electromagnet and it is having negligible air gap, in that case we have maximum inductance for the magnetic circuit. Now what we have found is that when we are talking about the lambda versus I plane, the Lmin and Lmax possibilities can be represented on these lines, which are effectively showing that with respect to a given excitation, how much flux linkage can be expected. And because any system has maximum limit on the flux linkage, so there is a possibility that after certain value of flux linkage, the core is going to saturate and the flux linkage is not going to move further to any appreciable value. So once the excitation is provided, the graph moves along this Lmin, and say we are keeping the current value at certain IC, which is a constant number, and allowing the plunger to move. So the plunger will move from position A to position B, and because it is hitting the lambda max boundary, it cannot go all the way up to this L max line, and this is where it will be fixing the lambda max value. Now if we allow the current to fall down, if we remove and if we allow the plunger to move, so it has moved to this second position and this is where this point B is corresponding to, and now if we allow the current to fall down, the graph may take this new path to come back to origin, and because we are talking about soft magnetic material, the remnant magnetic field may not be there in appreciable magnitude. So effectively the work done by this whole system is the area confined within this loop OAB, and this forms the basis of special machines which are acting on the principle of variable reluctance. So this is the principle on which this plunger is moving, and we can make the system more like a motor where we have rotary arrangements. So we may have a stator where we are providing the coils. So there is saliency on the stator, projections on the stator where coils are wound. and typically these may be connected in series. So the terminals of the coil could be A bar. Now there could be a rotating point in the system, a rotating part in the system which is hinged in the middle, and it is free to rotate about this hinged point. So once again, if we provide the excitation, the rotating part will have tendency to move and get aligned towards the projections on the stator, projections on the outer structure. So this is a very primitive structure of what is called as switched reluctance motor. And because we are talking about very simple structure where we have two poles on the stator and two poles on the rotor, so it can be called as 2x2 SRM. Now if we see from the constructional point of view, a more practical SRM may look like this. So as said, there is a stator where the windings are formed, and it's more in concentric fashion. It's more like a lumped winding kind of structure, which is quite different from the machines what we have seen in our previous module, that is induction machine or permanent magnet synchronous machine. Then we have these windings are done on projections which are there on the stator, and the rotor structure does not include any winding. So it's only iron which is there with certain projections given on the rotor. So the cross section of the motor may look like this. So we can count here that in a practical scenario we may have several poles provided on the stator. So we may have 1, 2, 3, 4, 5, 6, and then on the rotor we may have 1, 2, 3, 4. So more practically we may have a 6x4 SRM. However, to understand the basic functionality of SRM, we would go back to the 2x2 structure to understand how exactly the torque is generated in the machine and how we are making it operate with the excitation. So what we are finding is that once again, similar to our C-core electromagnet structure, we have two values for inductance provided over here. We have position which is completely unaligned, and we have the second position which is completely aligned. So which means we are going to have inductance values which are quite different. So in case of unaligned, we are going to have maximum reluctance, and hence we have minimum value of inductance. In case of aligned structure, we have minimum value of reluctance in the path, and hence the inductance value is maximum. Now this minimum and maximum are basically relative values for the given structure over here. Now if we try to see that in case of electromagnet, the work done is basically the change in energy what we have got. So which means it can be represented like this. So in first condition we have the core energy stored as L min I square, and in the second position we have L max I square, and thus the difference in this is basically almost the area given by this OAB region is the mechanical work done by the system. Now, if we want to understand the torque, this basically we need to take the derivative of this co-energy with respect to the angle, with respect to theta, mechanical position. So because we are dealing with system where the current excitation is not changing for the different positions of the rotor, so effectively we have torque for the system given by I square R times of rate of change of inductance with respect to the mechanical angle. So this gives the important factor for the SRM on how and where we are going to have the current excitation and how to expect the torque generation from that. Now, if we analyze, if we try to plot the inductance with respect to the mechanical position theta, and we take this unaligned position as 0 degree, so we are going to have the inductance value varying between certain minimum and certain maximum values. And once this mechanical angle is changed by 90 degree, we are finding that the system is going to have maximum inductance. So we can mark this different mechanical angle positions 0, 90 degree, 180 degree and so on. So what we find basically is that with respect to these mechanical positions, the inductance is going to change from minimum to maximum and then maximum to minimum. And it will go on in a cycle. Now, if we keep the, if we try to see the rate of change of inductance, if we plot dou L by dou theta with respect to the mechanical angle, we are going to find almost a constant value, positive value for 0 to 90 degree. And then negative value for 90 to 180 degree. And once again 180 to 270, it is going to be positive and then it is going to come back to negative. So it is more like a repetitive pattern which we are going to have for dou L by dou theta. Now, if current excitation is provided in the coil in such a manner that current is, say, uniformly applied for all the different positions of theta, what we are going to find is that the torque developed in the system is going to be pulsating up and down based on the value of dou L by dou theta. So we are going to have torque which will be positive for first 90 degree and then negative for the next 90 degree and then positive for next 90 degree and so on. Which means that if we are trying to create a uniform torque, a positive average value of torque, it cannot be achieved with a uniform direction of current or with a uniform current for all mechanical positions. Now, it should be noted that if the current direction is also altered along with the torque, which means that we provide positive current for the positive dual by dou theta and negative current for negative dual by dou theta, still our torque is going to remain same. This is due to the reason that torque is proportional to I square times of half of dual by dou theta. So the any change in direction or polarity of the current is not going to affect the direction of torque. Hence, we need to have arrangement where we should be able to generate only a unipolar torque or unidirectional torque in order to maintain a unidirectional omega. So, practically what is followed is the current is applied only over the durations when torque is having a uniform direction. Dual by dou theta is having a uniform direction. For example, if we want to generate a positive torque, we are going to apply current only over the region where our dual by dou theta is positive. So current will be like a pulsed current given for 0 to 90 degree angle, and then it is brought down to 0, and then once again given for next 90 degree, say 180 to 270 and so on. And the result would be the torque generated by system is now going to become unidirectional. Though it is pulsating, still having a pulsating nature, but on an average, the torque is going to be positive. So, which would imply that we can have a positive value of mechanical speed generated in the system. So, this is the fundamental principle which is followed for operation of SRM. Now, because of the structure of the machine, because of the structure of the poles and how we are having the design for the machine, we may have a more uniform, a more smooth curve for the inductance. It may not have a triangular kind of a structure, but a more uniformly changing waveform. And sometimes it may happen that there may be reasons towards the element where inductance is not changing at all. So we may have flat bottoms for this curve. This may happen on account of the gap between the two poles. If we have large gap between the two pole and rotor pole is coming in between that, we may not see any appreciable change in the inductance for a large angle. Similarly, if we have the rotor pole size bigger than the stator pole, we may have flat topped surface as well. So, on account of all these constructional features, what we may end up getting is, instead of a square wave for the dual by dou theta, we may end up getting a quasi square wave for dual by dou theta. So we may have dual by dou theta varying in this manner. And hence, the current also should be applied, because there is no point in applying current where the change in inductance is not happening. So we cannot generate any torque unless there is change in inductance. So which is why it may be useless to apply current over the durations when the inductance is not having any variation. So our current pulse also must be truncated and must be matched with the dou L by dou theta variation. So effectively the torque would also get truncated and it will have shorter pulse. However, that will be unipolar in direction. So we'll still have the average value of torque going greater than 0. Now this is for a very basic 2x2 switch reluctance motor. We, as I said, may have a more practical machines, for example 6x4 SRM, where we are having 6 poles on the stator and 4 poles on the rotor. Now one of the questions may arise that when we are talking about switch reluctance motor, this motor has tendency to move in steps. So how to compute the step angle? So there are two things which we need to understand from the practical point of view when we are talking about the SRM which are having integer ratio for number of stator poles and number of rotor poles. These are not very common. However, such machines do exist and many a times they may have tendency to get stuck in one of the positions. So for example, if we are operating such machine and the speed is not very high, there are chances that the rotor may get stuck in the position 2 where it is completely aligned, and then to make it move it may take some manual intervention. On the other hand, when we are talking about structure which is where the ratio of ns by nr or nr by ns is not integer, for example 6/4, the possibility of getting locked in one such situation is not there. So there are options available through which the machine can be excited and it will operate in automatic manner or on its own. So what we can say that one way to compute the step angle is to, for machines which are having non-integer ratio for the number of poles, it could be difference between the angles found by the stator and rotor pole. So we have stator pole angle given by 360 by ns and we may have rotor pole angle given by 360 by nr, and then if we go for 6/4 machine it is going to be 360 by 6 and 360 by 4 and given like 30 degrees. So as we can see, the difference between the two angles for the stator pole and the rotor pole is 30 degree. So whether it's a 6/4 SRM or 4/6 SRM, it is applicable for both. However, for machines which are having integer ratio or even non-integer ratio, we can have another way of computing the step angle which can be given on basis of the number of phase and number of rotor poles. So we have step angle given by 360 divided by q times of nr. Now the question comes, how do we compute the number of phase on the given SRM? So number of poles are very clear. The number of projections which are visible on the rotor are counted as nr. So nr is equal to 4. However, to compute q, we need to see the structure of the machine and how the windings are connected. For example, in this particular structure, if we observe, we have 6 poles on the stator, and with respect to the rotor, two poles are basically completely aligned. So I can mark as this. So that goes for what is written as A minus and A plus. Now from here, if we consider that the rotor is rotating in the direction which is counterclockwise, what we find that the next set of coil which is going to be aligned is given by C and C minus. So we can mark this as next aligned. Whereas the third set of coil, or the last two poles what we see, as the rotor is moving away from this is moving towards the most unaligned position. So then we can see that there are three group of coils which are formed within this structure, and hence what can be said is that the coils which are having similar position, which are like completely aligned, can be combined together. So we can have a common terminal for these two, say A and A prime. So we can mark it like A and A prime. For the next set of coil, again we can have series connection. So maybe we can use a different color over here. And this can be marked as B and B prime. Then the last set of coil can be marked as C and C prime. It should be noted that because the torque production is independent of polarity of current, direction of current, therefore marking the terminals plus or minus is not going to make much difference in SRM. So what we are finding that based on the configuration of the coil, based on the structure of the machine and based on the position of the rotor, we can decide that how many phases are going to be there on the machine. So then for this particular structure, when we have three phases, Q can be written as 3, and thus we have step angle given by 360 divided by 3 times of 4, which is 30 degree. So this formula is applicable even for a 2 by 2 machine as well. So we can as well apply. So what we find over here again, the coils are in, there are only two poles and both are having similar scenario. Either it will be aligned together or unaligned together. So there is only one phase, single phase, which is given over there. So the step angle is basically going to be 180 degree. So what we say that this machine can move only in steps of 180 degree. Whereas a more practical machine will have smaller steps, for example 6 by 4, which is having 30 degree step angle. So we can have more complicated structure. For example, we can look for machines which are having say 8 by 12 pole structure. So in that case, The stator projections are shown like this, arrows going inward, and rotor projections can be taken as arrows going outward. Now, once again, we can work out in a similar manner, and we can figure out what is the step angle. And from the general understanding, what we can say that this is going to have -15 degree step angle. So this could be a more practical way of implementing the SRM machine. Now, going by understanding that if we have to provide such current for the machine, how are we going to achieve that? Now, as stated, for the six by four machine, let us first understand how the inductances and other properties are going to change as the rotor is moving, and then let us go on understanding the development of torque. So when we have say 6 by 4 SRM, and we have identified that there are three phases, namely A, B and C, there could be three inductance associated with this, which could be LA, LB and LC. Now, what we can find from this picture is that if I am drawing a line which corresponds to 0 degree, theta equals 0 degree mechanical, in this position the rotor is going to be aligned along the phase A, which is marked as 1. So I can write A and A prime. Now, as we move further, as the rotor starts moving, so we can show the rotor projections by arrows, so which are marked here in the position of theta equals 0. And what we find is that it will be aligned along A and A dash, which means LA is going to be at maximum inductance value for theta equals 0 degree. Now, as the rotor is moving, the B phase will get aligned once the rotor has taken an step angle of say 30 degree. So LB is going to be and LC is going to be Lmax at theta equals -30 degree. And these three inductances are going to repeat or going to follow the cyclic pattern with repetition cycle of 60 degree each. So for the 654 SRM, basically phases ABC are identified in the similar manner, and what we are finding that the inductances LA, LB and LC are going to have maximum and minimum values at different positions of the rotor. So if we keep the rotor at say 0 degree position, say at this along this horizontal axis, we are going to find that the coil AA dash is going to have maximum inductance. So LA is going to have maximum inductance in this position. However, once the rotor moves by 45 degree, the same coil will have minimum value. For LB, as the rotor moves at 30 degree position, it will have maximum value, and then 45 degree from there it is going to have minimum value. So at 75 degree it can be marked. For LC, because the rotor is 30 degree and the phase is 30 degree lagging behind, if we see with respect to the position theta equals to 0, so what we say that at minus 30 degree this is going to be perfectly aligned, and at 15 degree this is going to be perfectly unaligned. So hence the maximum and minimum values are tabulated for LA, LB and LC. The same is drawn over here. We have LA going from maximum to minimum from 0 degree to 45 degree, and then rising again to maximum value up to at 90 degree, and then so on. Similarly, LB, which is at some middle value at theta 0, is aligned at 30 degree and then going completely unaligned at 75 degree, and so on. LC, which is once again at some middle value, however it is going to be unaligned at theta equals 15 degree, and is going to further be aligned at theta equals 60 degree. So what we understand that crudely the variation of LA, LB, LC is going to be like this. However, due to more practical designs, we are going to have much smoother curves compared to the triangular peak and valley. So if we try to draw the change in inductance of rate of change of inductance for the three phases, and we are considering only generation of torque in the positive direction, so we are going to consider only positive change in the inductance. So what we can have is basically we can take the middle regions of this waveform or of this graph, and we can ignore the endpoints of this peak and valleys. And so what we find that as we move along the theta, we are finding that we are going to have a positive dou LA by dou theta from 60 to almost 75 degree, and then we are going to have positive value for dou L B by dou theta from 90 degree to almost 105 degree. Similarly, if we go back, we are going to find a positive variation for dou L B by dou theta at from 0 to 15, and similarly for dou LC by dou theta, this is going to come from 30 degree to almost 45 degree. So we are finding that these phases, the excitation for these phases should be given in sequence to maintain a positive torque value altogether. So if we go on extending this plot, we'll find that each coil is basically excited after a gap of say 15 degree. So this is what the excitation angle, and then We can draw the current also, corresponding current also with a different color. So in this kind of structure, we are not having much overlap between the dou L by dou theta of two different phases. So we are going to have more pulsations on the torque generated from the machine. However, in other design, we may have some kind of overlap between the excitations of the between the variation of inductance and the excitation of the system to make the torque more uniform. Now, the question that how are we going to maintain a constant value of current for the given coil? So for the switch reluctance machine, because these coils are operating in independent manner, we need to have different set of arrangements for exciting these coils.